Hello, my name is John Capobianco, and today we're going to be talking about some artificial intelligence approaches to overcome hallucinations, incorrect answers, confidently incorrect artificial intelligence responses to prompts. This started with RAG, Retrieval Augmented Generation, which we are going to explore to level set and to start with an even playing field. From RAG, we can do advanced RAG, multi-query, and RAG fusion. And there's some other approaches, but I'm going to focus on multi-query and RAG fusion. And now an emerging approach known as Raptor. And Raptor is a tree-organized recursive approach and retrieval approach, similar to retrieval augmented generation, except we're going to retrieve from a tree that's built from the bottom up as opposed to the top down. So we're going to go through this journey together, and then I'm going to explore a tool that I've built using Raptor. And this is also all powered by Ollama and free open source tools. This code, the Packet Raptor code, is available on my GitHub. The tools that I'm using are available on GitHub. I just did a video prior to this, you may want to watch first, about free, private, secure AI with Ollama, but I'll explore that a little bit today in my Raptor approach. All right, so let's get going. So we're going to start with retrieval in the form of augmented generation. Now, the key here is that many LLM applications require user-specific data that is not part of the model's training set. Remember, we're working with pre-trained models, as in GPT, generative pre-trained transformers. These are all pre-trained. So if I want to ask it about packets, in my example, or routing tables, or specific documents, I need to supplicant, right? I need to supply and augment by retrieving from, in this case, a vector store, and in my case, a vector store, which is a database that stores the chunks of data and the embeddings, and we'll get through all this, but they store it in a place that we can retrieve from it. So when I ask it a question, it can retrieve vectors and chunks of text, often in the form of sentences or small blocks of text, to help the AI answer your question without hallucinating, without making up wild guesses. So we're going to start with RAG. We have a source. In my case, the source is JavaScript Object Notation, JSON. Now, the source could be and can be PDFs, PowerPoints, Word documents, Excel spreadsheets, GitHub repositories. You can chat with GitHub repositories, YouTube video transcripts, Twitter feeds, all kinds of stuff. We just need the appropriate loader. So I'm using a JSON loader because I'm taking a PCAP, a Wireshark packet capture, and using Python to turn the PCAP into JSON so I can load it into this LangChain. We're going to transform it. That is the process of making small chunks of text. I use a semantic transformer. So if we quickly pivot to the text splitting, we have some types of text splitting. Most people, and you can start with recursive, but that's your own defined characters, 200, 1000, however many characters you want to split on. I'm starting to play with the semantic chunker. Ooh, and I'm going to have to play with this new one here. I haven't seen this one. But it splits on sentences. So in JSON, recursive is probably good enough, but I'm still using the semantic splitter. So we have chunks of text. Now we need embeddings. Now, I'm going to talk about embeddings for a second. These are a list of floating point numbers, and there's text embedding models. We need a model. I have been paying for, up until this point, OpenAI embeddings, a cloud service that provides me the list of floating point numbers, the vectors. Think of this as a sphere. And in that sphere, there are three-dimensional floating point number coordinates that link to chunks of text, right? And we're going to store all that in our vector store. Now, there are a variety of vector stores, and I don't mean to exclude any, but the ones I've played with include Postgres, Redis, Weaviate, Pinecone, and Elastic from Elasticsearch, the Elk stack, Mongo, Atlas, and my favorite, and the one that I've landed on, is Chroma. Now, ChromaDB has some advantages in that it's private, it's in memory, it's in my computer, it's in my Docker container. It's secure in that way and confidential. It doesn't make any cloud calls at all. And it's fast because it resides in my memory and I can make it persistent. Now, that vector store, in my case, originally was a flat structure that stored the chunks of text and the embeddings, basic RAG. We're going to refer to that as basic RAG. Chunks of text, embeddings, store them, and then the retriever is where the LLM comes in, the large language model. I'm also going to say the SLM, the small language model, a language model. We use the AI here as the retriever. So when we ask a question, could you please help me understand this packet? It is going to retrieve from the vector store the appropriate coordinates and chunks of text to help augment the original prompt and generate a valid response. So we can look at all of these text embeddings, vector stores, retrievers, and indexing through LangChain. Now, let's talk about some advanced forms of RAG, and I have these in the reverse order. There is this wonderful RAG from scratch that you need to really look at, I think, if you're interested in this and doing a deeper dive. This is the RAG from scratch, and it explains different ways of doing this. And I've explained retrieval here in the top right corner. But if we look down, there is multi-query, and there is RAG Fusion. So let's talk about multi-query first. The idea here is that maybe humans aren't the best at asking questions. Or, right, we don't know what the human really wants to get out of the document or out of the packet capture in my case. So, user's original question comes in. We use AI, CQ123 here. We use AI to generate with a prompt. So my prompt is something like, please generate 3 additional questions that are similar in nature to the original user question, pass it the original user question, with varying levels of sophistication to extract the most out of the documents to help the user answer their original question. Something like this. We generate multiple questions with AI that we run everything against the vector store. So in this case, I would actually run 4 questions, the original question, and then the 3 AI-generated questions against the vector store, and then come up with the answer. Now, Fusion adds a ranking. See how there's a new funnel here at the end of this? We can use reciprocal ranking, and I'll explore this in a little bit more depth, to rank the answers. Now, a colleague of mine and I, and a few different colleagues, went a step further and thought, okay, instead of just reciprocally ranking them, what if we could then ask the AI one more time? So between the brain and the funnel, one more AI call that says, here's the original user's question. Here are 4 answers to similar questions and the original question. Considering everything I've presented you, could you synthesize and combine and create a super answer, the best answer given everything now that you know, given these questions we've asked you? And we present the user with a super answer. Now, a little bit more on RAG Fusion. RAG Fusion is a search methodology that aims to bridge the gap between traditional search paradigms, the original user's query, and the multifaceted dimension of human queries. Don't really know what the user's after here, right? So inspired by RAG, this project goes a step further by employing multiple query generation, what I just explained, and reciprocal rank fusion to re-rank the search results. And they give a wonderful cookbook here. Here's the reciprocal ranking function to re-rank your answers. And you can see here that we have the answer and the ranking score, right? So we can pick anything above, say, a 6. Consider that a good answer. Anything below a 5, throw it away, right? Or combine anything above a 6 into a super answer, right? Okay, so now pivoting further to the point of this document or this video, migrating from RAG to advanced RAG into Raptor, Recursive Abstractive Processing for a tree-organized retrieval. That's the key for me. It is recursive and abstractive, and it's going to process our data to generate a tree-organized structure that we store in the vector store for retrieval. Now, this is a wonderful paper, and I recommend you read it. But we're going to look at something that really, I think, resonated with me and resonates with normal human beings trying to figure out what the heck I'm talking about. Existing RAG approaches have flaws. The one we tackle the most is existing methods retrieve only a few short contiguous text chunks, which limits their ability to represent and leverage large-scale discourse structure. So, here it talks about the top K values. In my RAG code, when I do the retrieval, it's a semantic search against that spatial thing I talked about. And I say, give me your top X or K, in this case, values. Give me the top 10 or 25 or 100. The problem is, the more K values you include, the less you even need RAG. You might as well just send the original chunk of text in the new large context windows with AI. Send the whole thing in one context window instead of using RAG if you're going to return more than 10 or 25 or 100 K values. And here's the point. Let's consider the fairy tale of Cinderella. How did Cinderella reach her happy ending? Right? The top K values of small chunks of contiguous text will not contain enough context to answer that question, given if we uploaded the whole book of Cinderella. So, first things first, as a network engineer of 20 years, of someone who's built several large-scale data centers, I pivoted to data centers after my CCNP route switch, meaning I built an enterprise network, the enterprise portion, the campus, 45 buildings. And then the next project was to retrofit the data center into a new topology and with new hardware. So, right, in a 10-year project, we're going to do the campus, which is wireless and voice over IP, and the WAN, the wide area network. And then we're going to tackle the data center, right? This big, long project to retrofit everything with brand new state-of-the-art stuff. This is what a data center is organized as. We have a core. In networking, we call it the core. In this tree, we call it the root, the main central point, and notice it's 2 nodes, right? It spawns down into, in networking, we call it an aggregation layer. And I'm still going to call this an aggregation layer. I'm going to explain why in a minute. All the way at the bottom, we have our leaf nodes. Now in networking, the leaf nodes, underneath those is where we would plug in servers, equipment, mainframes, whatever, right? VMs. All that stuff would get connected at the leaf layer, providing a fully meshed, non-blocking topology in a tree all the way to the root, the core. Okay, so this appeals to me as a network engineer for that purpose, and I can really visualize and understand what's going on here. So from the bottom up, because that's in the AI, we're building from the bottom up, which in the networking world, we usually build from the top down. We're going to build our core access hosts in that order. But in terms of the AI, we're building this from the bottom up. At the bottom is the text chunks. That original thing from RAG, those text chunks, we're still going to use those. So imagine in your mind sentences and the story of Cinderella. The aggregation layer is going to be clustered groups of those text chunks. So maybe in the middle, 1, 4, and 5, is everything about the evil stepsisters. All the sentences and all the chunks of data related to the evil stepsisters is going to be clustered together in the middle at an aggregation layer. AI is going to summarize this ag layer and give us summary layers. And it's going to happen recursively until we run out of AI tokens, meaning until there's nothing left to summarize. So this is turtles all the way up. And we chunk and summarize, root layer. Now we have our root, and we've built our tree. Following the tree being built, we're going to store that entire tree, which is not a two-dimensional structure, into the flat layer in Chroma, but we still retain embeddings and text chunks, but it's the tree. And you can see the contents of the node on the far right here is the embeddings and the text and the children and the index kind of thing, right? So I found this cookbook, and here's another way to look at that. Can I open this in a new tab? Just the image? Yeah, okay, good. So the idea here is our raw documents. Those are the leaf nodes all the way on the left. That's going to be, in my case, little chunks of PCAP data, JSON. It could be sentences, again, with the Cinderella relevant, the Cinderella reference. Okay, so we're going to embed in cluster and create clusters of related leaf nodes. And then AI is going to create summaries of said clusters. We're then going to embed and cluster the clusters all the way up until we get to the root. Now, what's interesting is as we go from the most specific piece of information on the left, very most specific thing, the chunk or the sentence. As we head to the root, it's summary, highest level of abstraction possible, right? So maybe just a few sentences describing the packet. But as you get closer to the sentences, it's deeper and deeper analysis through those summary layers, right? Everything gets stored in the vector store that we can use as a retriever, just like we did all the way back in RAG. So let me just quickly go back here. This same idea, but in this tree format. So write vector store at the bottom and picture in your mind everything it's storing. Versus here, it's just the small chunks of text and the embeddings that are getting stored. All right, cool. So I have Packet Raptor. Bear with me, I need a drink. Okay. Now this is how simple I've tried to make this. Clone the Git repository right here. Copy that and type git clone and paste that in and clone it. Do Docker compose up, meaning you need Docker desktop is probably the path of least resistance here, is to just install Docker desktop, and then you can Docker compose up and bring up these 3 containers. After it's up, you're going to visit localhost 3002. So I'm going to show you here. So if I do cd and I do ls here, I have Packet Raptor. Packet Raptor. This is the result of git clone and that what you've copied and pasted. We go Docker compose up. Now, while this comes up, I'm going to look at some things for you programmers and developers out there. I have a Docker file I'm installing a few things: LangChain Experimental, LangChain Community, ChromaDB, jQuery, Streamlit for my UI, T-Shark to handle the PCAP to JSON translation, as well as PyShark. A few other tools here. I'm playing with visualizations that aren't quite working yet. You'll see them, and I haven't perfected them by any means. I'm still working out the visualization of the tree. And then fast embeddings is important. To divorce myself from ChatGPT and from paying for embeddings in the cloud and the privacy and security related to that, I'm going to use fast embeddings, fast embed, to do my embeddings locally and privately in my code. And my Docker Compose, on the topic of Docker, I have a network for Ollama, the AI service that I'm running, which is a server that runs in its own container. That's Ollama. I'm actually using my GPU here. You can comment this out and use CPU if you do not have a GPU. But if you do have a GPU, an RTX of any kind, I would leave this in because it allows for parallel execution in your GPU and processing offloading. I'm going to mount the volume and expose my ports for Ollama. Now this Ollama, I'm going to stop here. Let's go to ollama.com. I want you to look at this, right? Get up and running with large language models locally. And they have Llama 2, Code Llama, and more models. They have the GitHub repository here, and you just download it. For Linux, it's a quick curl. Windows, you download it. Mac OS, you download it. That provides you with the server capability. I've gone ahead, and there's one more tool. Now that is headless server, meaning it doesn't have any sort of front end. It's a fully API-driven server that you run, that you can run CLI commands against, or in my case, there is a open UI. Sorry, give me 1 second. Everything's freezing up because I got my container up. There is this WebUI called Open WebUI that is also open source. So I've combined those two into my own little container called Ollama with WebUI. Similar instructions. So for Packet Raptor, let's go to our WebUI here. And I'm going to log in. Now remember, this is all local. It's a private cloud. So even though you have to log in, it's not, I'm not logging into anything in the internet. It's localhost 3002. So I have already populated this myself. It doesn't come with any models. I'm going to install a new model and I'll show you how this is done. But I have 3 models installed. And you can see the size of these models. Mixtral's like 25 gigs. Llama 2 is 3.5 gigs. Phi 2, the small language model, is 1.5 gigs. I would even consider Llama 2 a small language model, to be honest with you. Mixtral is a large language model. So let's go to the gear, and we're going to go to models, and let's look for Gemma from Google, and we're going to go ahead and install that. Now, if we click here, we can see the library of models. So we're going to look at Gemma, and it's I would consider it a large language model, 5.2 gig. Could be small, somewhere in between, medium language model, right? So I'm going to pull that, and let's just let this finish. So while that finishes, let's take a look at this actual code here. I didn't mean to change anything in here. What did I change? So back in the code, the config toml is just to expose the port I want for my Streamlit. My script starts my Packet Raptor Pi as a Streamlit app. And now in the Packet Raptor, 22 lines of imports. And here's the chat with PCAP. And if we look at the init, is the important thing here. I'm taking the PCAP, but here, notice how I have these lines commented out. This is how I used to use it with ChatGPT as a paid service for my embeddings and my LLM. And now I'm using Fast Embed and Ollama locally throughout the rest of my code. Now that Ollama is the name of my container, and I have all three containers on the same network. So I have three containers running. If I show you Docker, I have my Packet Raptor, and I have my Ollama and my Ollama WebUI. So is that Gemma done yet? No, it's going to take a little bit more time. Well, we'll let this finish. So what happens in the code is we have this Streamlit upload and convert PCAP. And this presents a front end where the user uploads a PCAP. We convert it to JSON with a little function here, PCAP to JSON. And I'm using the T-Shark tool to turn my PCAP into JSON as a file. All right. After that, I'm actually making an API call to my Ollama. And when you run this locally, you'll have to do this. You'll have to go into the web GUI first, download the model or models that you want to play with before you can start using Packet Raptor. Because when we launch Packet Raptor, I'm asking you to pick the model you want to use for the rest of the session. So once that's done, we're going to actually go through and we're going to load that JSON, split it into chunks, set our root node, create our leaf nodes, build our tree, store it all in Chroma, and then set up our conversational retrieval chain. Now, all this code is available to you, but something like build the tree is pretty simple. But some of this code is actually pretty intense from a cookbook that I found to make summarizations and to help make the tree. I am trying to graph the tree, which I'm going to work on next. It doesn't look great right now, but I'll show you that. It's a work in progress. And this is almost done. And then we're going to visit localhost 8585. So Packet Raptor chat with Packet Raptor, Packet captures as a tree, and we're going to upload the PCAP file. This is almost done. We're going to let Gemma finish. I don't think I'll use Gemma because of its size. I'll probably just use Phi2 for this example, or Llama 2, or maybe both, to give you a sense on how the differences between some of the models. But I could try Gemma. It's going to take a little bit more time because it's a 5 gig model as opposed to Llama 2 or Phi2. So now it's going to download the rest of the SHA-2 digests and validate it, right? Verify the digest, and then import this model into our Ollama server. So that's what I've done here in this web GUI. Now this web GUI, fully functional as a ChatGPT substitute. I did that in my other video. We're not going to look at that. Okay, so now successfully downloaded, success, writing manifest, everything looks good. And if I check here, now I have the Gemma 4.8 gig. We might try Gemma. Let's give Gemma a try. So now in Packet Raptor, if I refresh the screen here, we're going to upload this ICMP in L2 L2TPV PCAP, excuse me. It's a tunnel PCAP that I found. The important part here is that I need a PCAP with more than just one packet capture. I found I couldn't use my dummy example of a single PCAP because it's not enough data to build a tree and auto summarize. So this one's 7.1K. And if we want to look at this PCAP, I can show you what this looks like in Wireshark. Hang on, where is it? And download. I don't know where it is. It doesn't matter. It doesn't matter. We're going to use AI to look at it. So let's go ahead and start with Llama 2. We're going to proceed to chat. And if you're using this, click proceed to chat twice. It's a Streamlit state thing. Anyway, drop down, pick your model, click proceed to chat twice. I'll work that bug out. All right, so here we go. This is really cool. So remember, keep in mind, where did that go? Keep in mind this image, right? From left to right. So what's happening here is that we created 45 leaf nodes from that PCAP, all right? It's summarized and clustered. Well, it clustered at this point 45 nodes into 6 clusters. So we've got 45 nodes at the bottom and then 6 clusters up above in the aggregation layer. Here is the fast embeddings, floating point numbers, right? The table, that 3D spatial awareness of the cluster nodes. And then here, I've just told it because we're making the summaries, why not print the summaries on the screen? Why not let the users see the AI's automated intelligence here? This is fully automated AI. I haven't asked it a question yet. We're just summarizing this up into a tree, right? So it knows the PCAP file contains several sections of data. And I'm starting to make the summaries for this L2TP, the layer 2 tunneling protocol packet. It continues to summarize. Look at all this great data. I haven't asked it a single question, and we have everything that you would ever want to know about this PCAP and this conversation without even getting to the question yet. And it's still summarizing. It's still working its way up the tree. This hasn't cost me anything because we're using Ollama and we're using Llama 2 in this case. So now I'm at the point where I've gotten down to 2 clusters and I'm out of embeddings. Okay, so I'm getting up in the tree here. And here is another summary at a higher level of the summary. And now I'm all the way into one node, the root. So now I'm storing it in Chroma. Here's that visualization that I'm still working on, by the way. This isn't great, I understand that, but what in my mind, what I'd like to do is have the root, the summary layer clusters, the leaf nodes visualized in an interactive tree here. Still working that out. Here's the automated AI analysis. And it's just incredible, right? I mean, look at all of this stuff. Look at all the frame information. I'm not going to bore you by reading all of this, obviously, but like we just upload the PCAP and we have absolutely everything you'd want to know about this conversation, right? And then finally, I can actually ask it things that maybe I didn't see here, or I don't know. Please help me understand this L2TP network conversation in like I'm 5, something like this. So now, okay, I'm going to crawl the tree and do cosine similarities to gather up from the tree relevant information that might help, right? I'm doing the retrieval portion now. So I'm retrieving it, and hopefully I'm going to get from that tree a nice pre-pended prompt that gets added to the user's question. So take the user's question and evaluate it against the tree, augment it with anything you can find in the tree, and then do the retrieval against the Chroma database to answer the question. Now, this does take a little bit of time, again, especially because I'm doing it locally and for free, but we will get an answer to my original question here. Help me understand this conversation like I'm 5 in just a second or two here. So again, reference document, reference cookbook on LangChain, Blob Master Cookbooks, Raptor, and the paper is found quite easily as well. You just Google it. And by the way, if you look in your logs here, it's kind of neat. You can actually see my actual GPU here. There's the 3.56 gig model size, right? It has 6.74 billion parameters, and it's Llama 2. I switch it over from CUDA over to my GPU, my RTX 2060 Super, offloading the layers to the GPU, and then I get the answers back. And these are all the API answers from Ollama. Now, it's still running, it's still churning here. And we'll just give it time. I wish I could take questions to fill the dead air here, but we are just waiting for the local LLM to answer my original question with the information from Chroma. We don't have any errors or anything yet. Everything is just running. We just have to be patient here. Okay, so I had a bit of a hiccup where it just hung up on me. It didn't actually process in the GPU. I don't know what happened. Can't explain it. Anyway, this is actually more exciting. So again, let's start at the top. Just as a quick refresher, I know I've been going for a while, but I'm going to go all the way to the top, and we're going to look at this page up here. Right, so because I've asked the question, I've lost the summaries up above. So it gives me the Raptor tree, which I'm going to fix, the automated AI analysis. This is without asking any questions. This is built up from the layers of the leaf nodes, the summary clusters of the summary clusters, all the way to root. And it gives us this great AI analysis of this PCAP. It's quite remarkable, right? So then we can ask it a question. In case the automated AI analysis doesn't reveal the truth to us, I've given a chat interface that we can follow up with questions. So when we hit send, I print everything to the screen so it's transparent. If you don't want to see all the noise, you can just comment out the st.write statements that write things like this. But after I send it, we're going to get the relevant nodes, which does all the cosine similarity searches. We're going to prime the text, generate the response, and here's the synthesized answer to my help me understand it like I'm 5. Now this is searching the vector store as a retriever, and in the vector store is the tree. So it gives us this, right, explains all this stuff like I'm 5, and it even gives me a little emoji at the end. Isn't that fun? And then the chat history here, I'm just dumping out everything that we can provide as a raw interface. And I'm probably going to not do that anymore. That's a lot of noise there. But anyway, that is Packet Raptor working. So it's pretty cool stuff. Let's finish up with some final thoughts. Okay, so I have Packet Buddy, and on Packet Buddy, I'm going to refactor it to use Ollama and be open source and free. That's the next thing I'm going to do, probably after this video, is to make Packet Buddy free and open source via Ollama. 2, I have Packet Raptor, which is the tree-organized approach, which we just saw today. Now, Packet Buddy, 1 to 3, 5, 10 packets works just fine. The more packets, the larger the PCAP, the more data, you're going to need a tree structure based on what we've explained here today. So I stand by Packet Buddy as a tool for 1 to 3, 5, 10, 25 packets in basic RAG with multi-query fusion. However, I like this tree approach. It's remarkable. I haven't even asked it a question, and the automated summaries through the layers of the tree that I understand as a network engineer because of the similar architecture, it really just extracts so much data as we go through each summary layer that I just show the user as we get to the final point where they can actually ask their question, which has most likely been answered in the automated analysis. So this is open source. I would like to see your PCAPs, because it's private and secure, right? Still be safe, still be right cautious. Make sure you look at my code, make sure you understand what you're doing. Um, I would be careful with production PCAPs or production network PCAPs. That is in your hands, not mine. Be careful, but play with some PCAPs. Wireshark actually has a whole library of sample PCAPs that you could download and play with freely and openly without any risk. So thanks again, and wonderful, wonderful progress from RAG to RAG Fusion to Raptor. Go develop some code with AI. It's free now.